So crystals have a regular arrangement of atoms, and that's called the crystalline lattice. So it's a little bit like a garden lattice, right? You can go to the garden store and you can buy these panels, right, that are a lattice. And then, they can be square like that, or sometimes they're more like that. And you can make fences out of them, you can grow plants on them. That's a lattice, okay? That's two-dimensional. What we're going to be looking at here is a three-dimensional lattice, but it's really the same idea. So here we're looking at, these are different atoms in a crystalline solid. And so the lattice points are going to be this, the places that are occupied by an atom, an ion, or a molecule. And then we're looking for the unit cell, which is the smallest unit of the crystal that can be repeated. You repeat that in all three dimensions and you get the crystal. So for this, and this is just two-dimensional, here if I take this and repeat it in all dimensions, I'm going to get the whole structure. If I tried to take that as my unit cell and repeated that, I wouldn't necessarily get the whole structure. So this is the unit cell we're looking at. And why do the particles arrange themselves like this? They do it because it's lower in energy. It's more stable for them. So there are a lot of different unit cells. These are just cubic, these are not just cubic, sorry. These are some of the unit cells. This one here is a cubic unit cell. A cubic unit cell is a cube, and a cube has a length and a width and a height that are all equal to each other, and they have right angles. And there are other three-dimensional solids that also show up as unit cells, but we're not going to worry about those guys. So we're going to look at some unit cells, and they're just really generic. In this section, some of the spheres, the atoms will have different colors, but that's just to make it easier to see what's going on. In all of these, all the atoms are the same atom. We talk about something called a coordination number, and that is the number of atoms that are directly touching a given atom. So what is it actually touching? That's the number of atoms that it can strongly interact with. You can also talk about packing efficiency, which is what percentage of that space is actually occupied by the atoms, as opposed to how much is the empty space in between. Because you can't pack a bunch of tennis balls together without having some empty space, right? It's just not possible. And there's a relationship here. If the coordination number is higher, the packing efficiency is also going to be higher. So this is what's called a simple cubic unit cell, where the corners of this cube are just in the center of atoms, and there's nothing else going on. This is a body-centered cubic, and this is face-centered cubic. And so here's all their numbers, etc., and we're going to talk about these one at a time. So in the simple cubic unit cell, we have one atom at each corner. So the corner of this cell is at the center of an atom. So if we're just looking at this cell, we're going to have to cut through the atoms, because each of the atoms is part of several different cells. So at this corner, we have 1/8 of an atom, and here is 1/8 and 1/8 and 1/8. You get the idea. So all together, there's one atom in this unit cell. If I took these pieces and assembled them, they would make one atom, one sphere. We can calculate the length of the edge from the radius of the atom, because as we can see here, this length is equal to the radius of the atom times 2. Here it's expanded out a little bit. This is what we were just looking at. This is with complete atoms, and the unit cell is inside them, essentially. And then this is spreading things out so that we can see the coordination number. If we look at this guy, right, he's directly touching this one, and the one below. That's 3. But then there's also one over here, and one up there, and one out in front. So each of these atoms is in direct contact with 6 other atoms. So that's the coordination number is 6. So let's look at this two-dimensional lattice and calculate the packing efficiency. Here, the packing efficiency for this one was 52%. So let's look at this one. So packing efficiency is the percentage that's occupied by the atoms. So it's the area of the atoms in 2 dimensions divided by the area of the unit cell times 100. In a 3-dimensional one, it's the volume of atoms divided by the total volume of the cell. If the atoms completely filled the cell, it would be 100%. There'd be no empty spaces. But like we mentioned, it's not possible with circles, right? So over here is the simple unit cell, right? And so we can look at this cell and say, well, how big is that? Ooh, that was bad. Let's try that again. Not much better. So we've got these atoms in here, right? And this distance is the radius of one atom. So from here, the center to one edge is the radius of one atom. So then the length of the side here is 2 times the radius. So I could calculate the area of the cell as the length times the width, which is 2r times 2r, or 4r squared. Yes? And then I can calculate the area of the circle. So this is the area of an atom. Because for a circle, the area is equal to pi r squared. So this is r, the area there is just pi r squared. So I'm going to put the area of the atom in up here, pi r squared, divided by the area of the unit cell, which was 4r squared, times 100. So very conveniently, the r squareds cancel out. I end up with pi over 4 times 100. My calculator is conveniently telling me 25 pi. Yep, that's not what I want to see. Where's that stupid button? Oh, I know. There's a setting on my calculator that will show things to you in different ways. Okay, so that is equal to 78.5%. So inside of this white square, 78.5% of that area is occupied by the atoms, and the rest of it is empty. The next type of unit cell is a body-centered unit cell. So we still have, we still have the center of atoms at each corner of our cube, but now we also have an atom smack dab in the middle of the cube. This is where the colors are different to make it easier to look at. This gold one is not a different kind of atom than the purple ones. It's the same kind, just for visual difference so we can see what's going on here. So here, these atoms are touching each other from one corner diagonally across to the other corner. So we can't just say, well, this edge length is 2r, because it's 2r plus a little bit. So there's all the geometry stuff, and this is the edge length down here. It's 4 times the radius divided by the square root of 3. And you do not need to memorize those. So different views, that's what we were looking at before. So those, the purple ones in the corners, that's 8/8 of atoms, so that's a total of 1 atom, plus the one in the middle. So this unit cell has 2 atoms in it. Here we see all the complete atoms at the corners, and here we're looking for the coordination number. How many different atoms is this one touching? It's touching 8 different atoms. So the coordination number is higher. The packing efficiency is also higher, 68% compared to 52%. So we can use the knowledge about the edge length and the type of crystal structure to calculate the density of an element, or to use the density. Well, actually, I'm getting ahead of myself. We're not talking about the density yet. Here, we're just going to talk about the volume of the unit cell. So this says we have a radius of, keep doing that, 138 picometers, and it's body-centered cubic unit cell, and they're asking us for the volume. So, body-centered, this is really tough to draw. It's got these guys at the corners, right? And then in the middle, there's that other one. That's the gold one in the middle. It's a very crude drawing. To calculate this volume, we need to know what the edge length is. So that was given here as 4r over the square root of 3. So this is 4 times r divided by the square root of 3. So the volume of that cell is going to be that edge length cubed. So 4 times r over the square root of 3, the whole thing to the 3rd power. So we can put in the other cubic unit cell we're going to talk about is the face-centered. And so here we have an atom centered on the face of this cube. Body-centered, the whole thing was in the middle. And here, one of them is centered on the face. So there's half of an atom on this face and half there and half there. Each of the sides has half of an atom. These are going to touch along this diagonal. So this diagonal is going to be 1r, 2r's, 3r's, 4r's. But we want to know the edge length. And so again, we're going to do some geometry there. And this is the edge length. It's 2 times the square root of 2 times pi. And I just want to point out that this is not 2 times the square root of 2 times r. That's not what it is. The r is not in there, right? It's 2 times the square root of 2 times r. This is not what it is. Again, looking at these other arrangements, so here we have 1/2 of an atom at each of the 6 faces of the cube, so that's a total of 3 atoms, plus the one that's spread out over the corners. So this has a total of 4 atoms inside of it. As you can see, looking at it with the entire atoms, it gets kind of muddy looking, right? And then looking at this, I don't even want to try to count that, but the coordination number is 12, and so that's a little higher, and the packing efficiency here is a little bit higher. So here's where we get to the density idea. So chromium crystallizes with a body-centered cubic unit cell. The radius of a chromium atom is 125 picometers. Calculate the density of solid crystalline chromium in grams per cubic centimeters. This is one of those critical thinking problems. There's lots of different ways to ask this question, or a question like this. So you can't just memorize a single formula and do it. Well, let's look at the numbers. I did it again. I've just been doing that like every single time. We're only given one number here, 125 picometers. But there's some other information here. Body-centered unit cubic cell. Body-centered cubic unit cell. That's a piece of information that's important, and this is chromium. So let's think about this. We want the density, so we can think about, well, what is density? Well, density is the mass of the thing divided by the volume. Could we calculate the volume of this unit cell? Sure, we did that previously, right? So we've got our unit cell here, and it's that body-centered, so it's 4r over the square root of 3. That's not an arm. It kind of looks like an arm. It's not an arm. 4r over the square root of 3. That's our edge length, this right here. So the volume is that cubed. Again, so now we're going to take the numerator and divide by the denominator. And this is going to give us 7.18 grams per cubic centimeter. Does that sound like a reasonable density for a metal? Mercury is 13.6 grams per cubic centimeter. Water is 1 gram per cubic centimeter. Any questions? Being able to do a calculation like this on an exam, I would expect that of, maybe A and B students. But if this just makes your head spin, don't worry about it, okay? This is not a big deal. And they won't make you do calculations like this on the final exam, okay? This is something we should be able to do, though. How many atoms are in the unit cell in the face-centered cubic structure? So we don't need to memorize this. We can think about it, okay? Maybe if I draw this bigger, it won't be quite so messy. So all of these have an atom in the corner, right? Those purple atoms, there's an eighth of an atom at each corner. So those add up to what? One atom. So one atom from that. And then here, this is face-centered. Do I have one atom in the middle or one on each face? One on each face, right? So I've got the face of one smack dab in the middle of this. This is cutting one in half, right? So there's half of an atom here, there's half up here, half down here. How many sides on a cube? 6? No, dice, 1, 2, 3, 4, 5, 6. So I have 6 of those times 1/2. So that's 3, right? 1 plus 3. So I've got 4 atoms. How many does the body-centered cubic unit cell have? 2. It's got the corner ones, which add up to 1, plus the whole one in the middle. And the simple cubic unit cell just has the guys on the corners, so how many atoms are in that one? 1. So this is the face-centered, and so the correct answer is 4. And not really any math involved with that. Another way to look at crystal structures is to think about laying the atoms down in layers and how those layers are aligned with each other. So you could think about, like packing oranges into a box, and how can you pack them in there so you get the most oranges, right? You want to have as small amount, the least amount of empty space as possible, so that when you ship these, they don't take up a lot of extra room, because that's going to cost extra money. So the simple cubic structure is where we have a layer of atoms in a square pattern, and then we have another layer of atoms, and the second atom is directly on top of the first atom. There's a lot of empty space here. And if you try this at home with marbles or tennis balls or something, you'll find out that the balls really don't want to be like this. Because this one is going to fall down into the divot between the ones on the bottom. So it's actually hard to pack something like that. And that square organization is also not as compact as it could be. So here, instead of having this row lining up with that row, they're staggered. So this guy can get in closer because it's coming into this little area here. So the second row is offset by half of an atom, and then this one is back in line with the original one. And so this is more efficient, and this is a close packing. Then we look at, well, how's the second layer going to go on? So we'll call that bottom layer A, and then we put a second layer on top. Well, we can put layer B so that it fits in the divots created by the lower ones. So these 3 atoms here, there's going to be a little lower place right here that another atom could sit in, right? So we're going to arrange these so that these are sitting in those divots, and that's going to be layer B. And then the third layer, we've got a choice now. That third layer can be lined up exactly with layer A. And so this has an A-B-A structure. And this is called hexagonal closest packing. This has a packing efficiency of 74%, a coordination number of 12, just like that face-centered, right? But here, this unit cell is not cubic, it's a hexagon. So this is the unit cell right here. It's hexagonal. These angles are not 90 degrees. Another way to do that is when we put that third layer on, we can arrange that so that this atom in layer C is not directly over any of the atoms in layer A. So this is offset. So now we have an A, B, C pattern. And this turns out to be exactly the same as the face-centered cubic unit cell. So this is showing how the layers are stacking up. You put those guys together, you tip it on its side, and you chop it up, and there's your face-centered cubic unit cell.